Yeah. So now we continue the previous lecture with the last two parts of the proof of Caratheodory theorem. So we recall we have proved that M is the collection of all mu star knives is a sigma algebra and mu star restricted to M is a measure. Now, first we will prove that, well, we know to extend from the semi-algebra to the algebra. So given a pre-measure on an algebra, so rho is a pre-measure on an algebra, close 0 comma infinity, and since the algebra is also a semi-algebra, so let the first part take the mu star constructed by rho by the analogous formula by infimums, and then do the first Caratheodory extension. Then there exists an M of all mu star knives, which is a sigma algebra, and mu star restricted to that is a measure. First of all thing is mu star restricted to A. Mu star can be restricted anywhere, right? It is dependent on the whole power set of X. Is rho. Add mu and A is contained in M, and A is contained in M. This is the second part of the theorem. This completes the existence, that it actually extends the pre-measure on an algebra to a measure on a sigma algebra that contains the sigma algebra generated by A. Right. So the first part, we will show that mu star A is equal to rho. So suppose E belongs to A, then suppose ANs be a cover, so that AN take this, then E intersection AN union is E. Since rho is a pre-measure and since the countable union is E, so actually you have to disjointify this. So take a disjoint union. So take ANs and disjointify it first. Disjoint union this, and then this is also a disjoint union, and you can disjointify it so that the disjoint union A subset of E, and upon disjointifying the elements still remain in the algebras because it is closed under complements of finite intersections. So then rho of disjoint union E intersection N, which is equal to rho E, is summation rho of, since they are in the sigma algebra, this is rho of E intersection N. Why? Because rho is a pre-measure, and so mu star E, mu star E is less than equal to summation rho intersection N, which is nothing but, from before it is rho of A, rho of E, and the other side is trivial because okay, so we showed this one. Okay, no, not this actually, we have to do something different. This proof is not correct. So this part is actually trivial, this inequality, because since E covers itself, then mu star of E is less than equal to rho E. So what we can do is this, that is a standard disjointification technique. So take rho star. So suppose rho star is fine. If it is infinite, then it is done. The rho is must be infinite and they are same. Take an epsilon greater than 0. Then there is an collection of rho n's, so that rho n's cover this, and summation rho n is this. If rho n's covered this, then n intersection e also cover this. Then union n intersection e is equal to e. And you can check easily for an algebra this is true. That's why we need an algebra, that rho of a minus b, am I saying it correct? I mean, if a is subset of b, sorry, if a is subset of b, then rho of a is less than equal to rho of b, because so because if a and b are both in the algebra, then b minus a union a is in the algebra, and you can break it, and from there it follows. So this is greater than equal to summation rho n intersection, and by the thing that we did just before, this is equal to rho of e, since it is a pre-measure. So this is true for all epsilon. So rho star mu star e is greater than equal to rho. So the first part is done. Second, now suppose we have to show a belongs to M. So mu star, take any arbitrary e, then mu star e plus epsilon. So if mu star e is infinite, so mu star e is infinite, then it is done, because that inequality will always hold, that mu star is greater than equal to that. So take an epsilon greater than 0, assume mu star is finite, then you will get elements in the algebra such that ans, so that mu, this is true, and union n covers. Now this can be written as summation, sorry, and this will be rho, and this will be rho. This can be written as summation rho of an intersection a, since they are in the algebra and it's a pre-measure, equal to summation rho of an intersection a complement. Now since rho of an intersection a covers e intersection a, so this is greater than mu star e intersection a. Similar design, since they are in the algebra, this covers mu star e intersection a complement. Since it is true for arbitrary epsilon, it is true for all, hence we are done. So the first part is proven. Now that we will prove, and we will use monotone class theorem for it, that is, this is not true if it is not sigma finite. We will give an example. That is, this extension is unique up to the sigma algebra generated by the algebra. Why? Well, if A is a sigma finite algebra, sigma finite, I mean x comma a comma rho is a sigma finite pre-measure space, let's call this, not a standard notation, I don't know, pre-measure space. Then that is, x can be written as countable union of elements, of finite pre-measure elements in the algebra. Then if this is a very general theorem, not well, yeah, this is a very general theorem, but we combine all this to Caratheodory. There may be books where only the first part is called Caratheodory extension. When and if mu1 and mu2 be measures on the algebra generated by A such that mu1 restricted to A equal to mu2 restricted to A equal to rho, then mu1 equal to mu2 on F. And this ends the theorem. So for this we will use the result that we proved in the first lecture, that is monotone class theorem. Let me recall it. Monotone class theorem says that if A is an algebra, the sigma algebra generated by it and the monotone class generated by it coincide. So we will prove the result for a monotone class, and since it is same as the sigma algebra, we are done. Now, first assume x a comma a is a not sigma finite, it is a finite pre-measure space. That is rho of x is finite. That is rho of x is finite. So mu1 and mu2 are finite measures because mu1 mu2 restricted to A is rho. Define G. This is called a good search principle. All such A belongs to FA such that mu1 A bad notation. Also E belongs to FA such that mu1 E equal to mu2. Clearly the algebra is here. Clearly the algebra is contained in G. Secondly, if ENs increase up to E, then by continuity from below, mu1 En increases to mu1 E, which is equal to mu2 En, which increases up to mu2 E. So mu1 E is equal to mu2 E. So by from continued increasing chains, the limit is in here. And for decreasing, we need the finite case. For decreasing thing, we need the finite case. So if En, since they are finite measures, En decreases to E, then we can apply continuity from above if and only if it is a finite, if and only if this measure is finite. So this decreases to mu1 E, which is equal to mu2 En, which decreases to mu2 E, and which is same. So it is true for every. So G is a monotone class containing the algebra. So and it contains f of A, which is same as m of A. So G is a monotone class generated by the algebra. So G is contained in f of A, and G contains m of A, that is f of A. So G is equal to f of A. This done the finite measures case. Now you do for the sigma finite measures case. So assume An is disjoint union of X is disjoint union of An such that rho of An is finite. Well, sigma finite says is union, but you can disjointify it, and still since the union is same and they are subsets, so still they will have finite measures, so you can do this. Define Gn to be exactly similar manner. All such E belongs to Fa such that mu1 E intersection N is equal to mu2 E intersection. Okay. Since N is in the algebra, A is contained inside Gn. A is contained inside Gn, and continuity from below doesn't matter. Continuity from above will happen because An's are finite measure. So all this Gn, exact same logic as before, is equal to f of A. Now we will show it for all. Mu1 E since it is disjoint and its a measure is summation of mu1 E intersection ans, which is equal to summation mu1 mu2 E intersection a, and this is equal to mu2. Hence the Caratheodory uniqueness extension theorem is proved, and we see how important sigma finiteness is while doing the proof. So let's give an example such that when sigma finiteness is actually necessary to do the proof. So take Q and take the algebra. Well, it's kind of like it is called a trace algebra. So on R we have the algebra. So we have the God-given semi-closed intervals or open closed intervals. We take this is semi-algebra on R. So restrict it to Q. That is, take all intersection with Q. So this is a semi-algebra on R. You can verify. Intersection is trivial, and intersection is trivial, but the complement part is what makes let's see. So intersection Q complement, so this is A comma B complement union Q complement. So this can be written as finite intersection of the semi-algebra. So this can be written as A1 comma B1. Since it is semi-algebra, we can exactly write how many, but AK BK. Union Q complement. Okay, so why is this semi-algebra? So this is actually may not be a semi-algebra. So this is actually restricting the semi-algebra to Q, but you can check one thing, that if A is an algebra on some X and Y is a subset of X, then A intersection Y, A belongs to the algebra, is an algebra on Y. So the only problem is complements. So A complement intersection. So this is A complement union Y complement. So A complement is there in the sigma algebra. A complement is here, so we need to show, is this question true, that if A is a algebra and this is, sorry, other side equation, the A intersection A gamma is a algebra, sigma algebra, an algebra here. It is true. This is called a trace algebra, but okay, I'm sorry, what I am doing, I have to take the complement here. So I mean, we have to take the complement in here. I am taking the complement in the entire thing. So this is A complement. This is A complement. Yeah. So yeah, it's an algebra. It will actually be a semi-algebra also. Sorry, bad mistake. So okay. So take S to be. So we know the algebra generated by the given semi-algebra. So S is the God-given semi-algebra of all semi-open closed intervals. Take AS and restrict it to Q. Then it's an algebra on Q. What are the elements of the algebra? Let's call this AQ. All such disjoint unions of finite disjoint unions of this intersection Q, where these belongs to the algebra. I am not writing it repeatedly. So first is sigma algebra generated by this. F of A Q of S is a power set of S. Is the power set of Q. That is quite trivial because take any Q in capital this and take Q minus 1 by N comma Q intersection Q. So these are inside AQS. So these are inside the sigma algebra. So this countable intersection is inside the sigma algebra, and this is nothing but Q. And since every singleton element is there and Q is countable, so every subset of Q is there. So this is power set of Q. Second, second is this is not sigma finite. So lambda is a God-given function here. So lambda is a pre-measure. So okay. Define mu1 to be a measure on power set of Q. So to be in this form, mu1 of phi equal to 0 and mu1 of any other set is infinity. And the other measure, probably counting measure will be. Another measure is a counting measure. Now, it's clear that mu c and mu1 don't coincide on power set of Q, because finite sets is just a different thing. But mu1 and mu c coincide on the algebra. So it's a restriction to algebra, so it's a pre-measure. These are measures and it's a restriction to algebra, so it's a pre-measure. Why it's on the restriction to this is same, because every element of this form, since Q is dense in R, every element of this form is on either phi or contains infinitely many elements of Q. So mu c of that has to be infinite. So it coincides on the algebra, but it does not coincide of the sigma algebra. Why did we have this problem? Because this measure is not sigma finite. I mean, you can't write Q. You can write Q as a countable union of finite measure sets, but not through AQS, because AQS does not have any finite measure except phi. So this is an example where to show that sigma finiteness is necessary to make this uniqueness. So suppose you take AQS, and so suppose you took AQS and defined the pre-measure like this. There was no restriction for pre-measure to be anything. So there would have been extensions, and we saw two different extensions that are not unique, but they are coincide on this. So this third theorem fails if it is not a sigma finite measure space, and this ends actually the entire Caratheodory theorem construction.